we're starting with an example, and the example is about lossy media and power. Here's the problem. A uniform plane wave is traveling in seawater. So we're already under the water, and the plane wave, we're given the magnetic field at z equals 0, and z is increasing downward, so that's the plus z direction. And we're saying that the magnetic field in the z equals 0 plane is y hat 100 cosine of 2 pi times 10 to the third t plus 15 degrees. And we're asked to find, first of all, phasor expressions for E and H as a function of position. So, first of all, phasor expressions for E and H. All right, how do we get those? We're going to need to know everything about the plane wave propagating in seawater. So we need to know all the wave parameters. We're given that the relative dielectric constant is 80 and the relative permeability is 1 and the conductivity is 4 Siemens per meter. So then, the question is it a good dielectric? Is it a good conductor? Let's find out. And the way that we find out is we figure out what is epsilon double prime and what are epsilon prime and how big is that number. So epsilon double prime here is sigma over omega, which is 4 divided by 2 pi times 10 to the third. And epsilon prime is 80 times epsilon naught, which is 8.85 times 10 to the minus 12. You can tell by looking that epsilon double prime here is definitely more than, that's not 10 to the 13th, that's 10 to the third. That epsilon double prime is definitely more than 100 times larger than epsilon prime, so that makes it a good conductor. Since it's a good conductor, we can use all the good conductor expressions, the approximate expressions for the propagation parameters. So that means that gamma is 1 plus j times square root of omega mu sigma over 2. And that's going to be alpha plus j beta, and those are going to be equal in magnitude, the real and imaginary parts of the propagation constant. And we find that that is 1 plus j times 0.1257 in inverse meters. So that's our propagation constant. We also need to know the intrinsic impedance of the seawater. And that turns out to be, if you plug all those numbers into MATLAB, well, the expression that we're going to use is 1 plus j alpha over sigma. And that is all from table 7-1. So what we get for eta is that 1 plus j times 0.0314. So based on what we know from that, we can now write an expression for the magnetic field as a function of position and time, and then we can convert it to a phasor. So it's y-directed, it has amplitude of 100. It is cosine of 2 pi times 10 to the third t. Now it's propagating in the plus z direction because we defined the plus z direction to be down. So it's going to have minus beta z, and beta here is going to be 0.1257. So that's minus 0.1257 z plus its original phase, so plus 15 degrees. And what was not included in our original expression, but which we definitely need to include, is the attenuation with distance. So we also have an e to the minus alpha z. I'm going to put in the value of alpha since we have it. So e to the minus 0.1257 z. If we want to write that in the phasor domain, all we have to do is convert this cosine into a phasor. So the phasor version, h of z, is y hat 100, moving this exponential decay out to the front because that's usually where it goes. So e to the minus 0.1257 z. And then we're going to do the position-dependent phase and this 15 degrees here. So e to the minus parentheses j 0.1257 z minus 15 degrees. This is a minus here and a plus here because we've got a minus sign in the front. So that accounts for the difference in sign between those two terms. So there's our phasor magnetic field. Our electric field is related to the magnetic field by the amplitude of the electric field is just the intrinsic impedance times the amplitude of the magnetic field. So, how do we work that out? E of z, we also need a direction for this field. So if h is in the y direction, we need E cross H to be pointed in the direction of propagation. E cross H along K. And the direction of propagation here is z hat. H is y directed, so E must be x directed. So, first of all, we got our x unit vector here. We're going to multiply eta times the amplitude of h. So eta up here was 1 plus j times 0.0314. So that's going to be x hat times 1 plus j times 3.14. We're going to have the same position-dependent attenuation term, so e to the minus 0.1257 z, and then we're going to have the same phase term, so e to the minus 0.1257 z minus 15 degrees. That is our phasor electric field and our phasor magnetic field. I'll draw squares around them so they stand out nice and you can see them. And that was part 1 of that example. For the next part, we're asked to find the depth at which the magnitude of E as a function of position is 10% of original value. The only thing that is changing the electric field amplitude with position is this attenuation term right here. At z equals 0, the electric field has amplitude, whatever this amplitude is, magnitude of 1 plus j times 3.14. I guess that would be roughly pi root 2. So what we need to do is say e to the minus 0.1257 times d, that's our depth, equals 0.1. And then we have to solve for d. So we take the natural log of both sides. And we get that d is the natural log of 0.1 divided by minus 0.1257, which works out to 18.3 meters. Lastly, part 3 is find the power dissipated per unit area in the seawater between z equals 0 and z equals that depth that we found in part 2. Fundamentally, what we're trying to do here is we have an expression in the Poynting vector for the power carried by this wave per unit area. And we know that the power in minus the power out has to equal the amount of power dissipated per unit area. I'm not writing it as S dissipated because it's not really a Poynting vector anymore. But the difference between these two time average Poynting vectors will get us the amount of power per unit area that's being dissipated. And we already know, because of the constraints that we put on the value of the depth, that this power in minus power out is actually power in minus 0.1 times power in. So that just equals 0.9 times power in. I'm using these magnitude bars everywhere because Poynting vectors are in fact vectors. So they're real, but they have a direction, and they're all pointing in the same direction, so we really only care about their amplitudes. So we want to know the total amount of power dissipated per unit area. First, we have to find the amount of power that went in, and then we have to multiply by 0.9. How do we do that? S in is equal to, it's going to be along the direction of propagation, 1/2 the real part. We're doing the time average Poynting vector, obviously. E cross H star. Since this is a plane wave, though, we know that E cross H star is also equal to magnitude of E squared over eta, and that's also equal to magnitude of H squared times eta, because of the relationships between E and H. So since the magnitude of H is 100, we're going to use that. And then we get that the incident power per unit area is 1/2 the real part of 100 squared times, where's eta again? 1 plus j times 0.0314. If you solve that out, what you get is 100, S in has a magnitude of 157 watts per meter squared. So then if we want to know the power dissipated, S dis, even though I just said I wasn't going to do that, is equal to 0.9 times S in, which is equal to 141.3 watts per meter squared.